Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electricity and magnetism, and so far we were discussing about the basic concepts related to electric potential difference. So in this video we are going to discuss about electric potential due to a point charge and a group of point charges. So first we'll discuss about the electric potential due to a point charge, and then we'll extend that discussion to the same when there are multiple point charges located in space and we have to find out the electric potential at any specific point. So for that, let us say that here we have a charge plus Q which is located at O, which is the source charge, the source of electric field, and we have a test charge. Let's say we have a unit test charge. If we say unit positive test charge Q0 is equal to 1 coulomb, okay, that we have. And here what we have to do is that we have to move this test charge against the electric field of Q and move it to various points, okay, A, B, P, like that. Now here we know that the electric field, okay, produced by the source charge, it is from left to right, okay, both of them are positive, and hence there will be a repulsive force, coulombic force between them. And here, in order to move this test charge Q0 from right to left, there has to be some work which has to be done against this force. So the force acting on this test charge, okay, it is F is equal to Q0 E, this, because E is equal to F by Q0, where F is the coulombic force and Q0 is the test charge, E is the electric field. So in order to move this test charge against the electric field, work which has to be done in the opposite direction, okay. So a negative or the force in the negative direction or opposite direction has to be exerted, so that force will be minus Q0 E, okay, minus Q0 E, because it has to be moved opposite to the coulombic force. So again we know work is equal to force into displacement, okay, work is equal to force into displacement. So here let us say that the charge is at A, the test charge is at A, and it is moved by a very small distance dx from A to B. So for that, the small amount of work which has to be done, let's say we call that dW, that will be the force minus Q0E, the opposite force, multiplied with the displacement, which is dx. dW is equal to minus Q0E dx. Q0 is equal to 1 coulomb, so we can replace Q0 with 1 coulomb and it will be simply minus E dx, minus E dx. Now from this A, let us say this charge has to be moved to this point P, okay, from infinity to A first it has to be moved, and then from A to P. So in that case, the total work which has to be done in moving the charge from infinity to P will be from infinity to A, like this, from infinity the potential energy is 0, from infinity to A, then from A to B the small displacement dx, then again in order to move this charge to the point P, the total work which has to be done, is equal to integration of the same force into displacement from infinity to r, because the distance of this point P from the source charge is r. Okay, this. Now we know that the expression of electric field intensity is equal to 1 by 4 pi epsilon 0 q by r square. Okay, q by r square, or in terms of this, okay, where displacement is considered as x or the distance is considered as x, we can modify it as E is equal to 1 by 4 pi epsilon 0 q by x square. X is simply the distance between two charges in terms of Coulomb's law. So here we'll replace E with 1 by 4 pi epsilon 0 q by x square. So it will be integration from minus phi to r minus 1 by 4 pi epsilon 0 q by x square. Simply I am substituting E with this value. Okay, so it will be dx. So 1 by 4 pi epsilon 0 q, they are all constants, so they will come outside. So it will be minus q by 4 pi epsilon 0 phi to r. This is phi only. Okay, this is phi. Okay, so it will be 1 by x square dx. Okay, so this will be, let us write it here, minus q by 4 pi epsilon 0, so minus 1 by minus 1 r and phi, that is minus q by 4 pi epsilon 0 minus 1 by r minus this 1 by phi. 1 by phi is 0, so it is simply q by 4 pi epsilon 0 r. That is the work done. Okay, that is the work done. Work done is equal to q by 4 pi epsilon 0 r. This q by 4 pi epsilon 0 r. That is the work done. Now we know that the potential at any point, is the work done in moving the charge from infinity to that point divided by the test charge itself. Okay, so here the work done in moving the charge from infinity to this point P, which is at a distance of r from O, is given by infinity to P, is q by 4 pi epsilon 0 r, which we just calculated here, this q by 4 pi epsilon 0 r, and q0 is 1 coulomb. Test charge is positive 1 coulomb. So Vp will be q by 4 pi epsilon 0 r divided by 1 coulomb, which is simply q by 4 pi epsilon 0 r. That is the expression of electric potential due to a single point charge, which is this q by 4 pi epsilon 0 r. So here q is the charge, the source charge. Okay, then we have epsilon 0 is the permittivity of free space, the absolute permittivity, and r is the distance between the source charge and the test charge, which is located at any point in space. Okay, this here the test charge is moved from infinity to P. Distance between the source charge and the test charge q0 is r. So in terms of that, the expression of electric potential is Q by 4 pi epsilon 0 R. This is for a positive unit test charge. Okay, this. Now, if we extend this discussion for single point charge to multiple point charges which are located in space. So for that, let us say we have a number of point charges Q1, Q2, Q3, Q4 up to Qn located in space, and they are at a distance of R1, R2, R3 and R4 from the point P where we have to calculate the electric potential. So here again the principle of superposition will come into play. Superposition principle was also utilized in the determination of electric field intensity, and the same thing will also be helpful in determination of electric potential at due to multiple point charges. So the total potential, okay, here at point P, the total potential is the sum of the potentials due to the individual point charges. That is for V1 due to Q1, V2 due to Q2, V3 due to Q3, V4 due to Q4 and so on up to the nth charge. So here V1, following this relationship between electric potential due to a particular charge, point charge, V1 is equal to Q1 by 4 pi epsilon 0 R1. Okay, V1 is Q1 by 4 pi epsilon 0 R1. Similarly, V2 is equal to Q2 by 4 pi epsilon 0 R2. Similarly, V3 is equal to Q3 by 4 pi epsilon 0 R3. V4 is Q4 by 4 pi epsilon 0 R4. So the total potential at P, it will be given by the total potential at P, okay, is V1 plus V2 plus V3 plus V4 due to the nth charge. So it is simply Q1 by 4 pi epsilon 0 R1 plus Q2 by 4 pi epsilon 0 R2 and so on up to the nth charge Qn by 4 pi epsilon 0 Rn. This. From this, if we take 1 by 4 pi epsilon 0 common, okay, if we take 1 by 4 pi epsilon 0 common from this, then it will be Q1 by R1, Q2 by R2 up to the nth one, which is Qn by Rn. This. Or we can express it as Vpt due to multiple point charges 1 by 4 pi epsilon 0 summation from I equals to 1 to n Qi by Ri. This is the expression for electric potential due to a group of point charges, which is this. Okay, 1 by 4 pi epsilon 0 I equals to 1 to the nth charge Qi by Ri. So we simply, what we did, we took the discussion from a single point charge, the expression, and we extended it to multiple point charges using the superposition principles, where the electric potentials due to multiple point charges located at different locations in space with respect to their distance from the point where the electric potential has to be calculated or measured, and we just added them together and we got the result. Okay, this. So here we have discussed about electric potential due to a single point charge and electric potential due to group of multiple point charges. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.